All right, thanks for coming. My name is Daniel Wang. I'm the founder and CEO of Loopring. So today I'm going to talk about Loopring 3.0, which uses zero-knowledge proof to scale. So scalability is something we want to achieve, but not privacy. Okay. So Loopring is a project that started back in August 2017. So we focus on one thing and one thing only, which is the order-based DEX protocol. So over the last year and a half, we have deployed 3 major versions of the protocol on top of Ethereum. We introduced some cool features, including the ring matching, dual authoring to prevent front running, and some very cool fee models. Unfortunately, the protocol is not widely adopted. So we ask ourselves why. What's missing in the current implementation? So I think it really boils down like 3 issues. So right now the user experience is not good. It's not an easy fix, right? And one of those issues in this area is the trading the finality. So for market makers, they really want to see their settlements got finalized as soon as possible, so that they can start submitting new orders. But right now on Ethereum, you have to wait for like 15 seconds also to make sure the settlement is built into the blocks. But sometimes it takes really even longer, right? The second one and the third one is even a bigger problem, right? So the throughput is so low, the gas cost is so high. I'm going to show you some numbers. So our goal in 3.0 is to make sure we achieve the following. So the settlement should be finalized as soon as possible. This finality is not actually the blockchain level finality. It should be like a centralized exchange level finality. So it can be reverted, but it's not. You are fairly certain that the settlement is done. And then we want to achieve higher throughput, lower cost, and then shouldn't have any trade-off in security. So we don't want to use side chains, other cool stuff to achieve throughput by sacrificing security. All right. So with the previous versions, this is the number, right? So we can put about 26 settlements in one Ethereum block. So you can do the math, right? Right now it's like less than 2 trades per second on the Ethereum mainnet. I think this is true even for our competitors, right? More or less. The cost is even a bigger problem right here. So it depends on the price of Ether. The cost is probably 10 to 20 cents, right? Imagine when we have the bullish market, the cost is about 30 or even more, 20 or even more. So with Loopring 3.0, we really have 2 options. First is called with data availability. So what does that mean? So with on-chain data availability means any third party can depends on the Ethereum blockchain can reconstruct the state of the DEX for any given moment in the history. So you don't really have to trust anyone, right? Because you can reconstruct the state, which is basically the Merkle tree, then you have the way to generate the Merkle proof, which will be used by anyone to claim the asset in the DEX. So with on-chain data availability, we managed to put 1,800 settlements in one Ethereum block. So this means like 120 trades per second. Okay, and the cost for gas is less than 0.2 US cents. This is assume that the price is 190. Right now it's a little bit higher, right? But it's not compared to 13 cents is nothing, right? The other one is, we turn off the on-chain data availability. So we find another, DEX operators, they can find another option to provide the data. For example, they find the auditing firm, say, okay, we are going to publish the data on a daily basis, or put it on IPFS, something like that. So there are some risks, right? For normal users, it's possible that they don't have access to the data in real time, and sometimes, if the DEX operator do not really honor their promise, maybe user will not have access to the data at all. But if we turn this off, we can put like 7,000 transactions or settlements in one Ethereum block. So this is the current result. So the cost is even lower, right? Less than, it's about 0.05 cent. There are now off-chain costs. So previously, when we do 1.0, 2.0, we put everything on chain. So Loopring protocol is basically a set of smart contracts. Now we have off-chain parts, right? We have the code to maintain the off-chain Merkle tree, and to I think most importantly, we have some program called Prover that has to generate a zero-knowledge proof. So we tried Amazon AWS with this 48-core Xeon processor with a lot of memories. So for a virtual block that has 512 trees, it takes less than an hour to generate. So the price is $6 per hour. If we use some cloud service in China, this price is going to be like half, right? Like $3 per hour. So right now with AWS, the price or the cost to generate the proof for each settlement is less than 0.9 cent, right? This is irrelevant. This has nothing to do with the Ether cost. It's just purely the cloud service cost. So if we combine those numbers together, we get the final throughput and cost, right? So it's 120 for with data availability, 1 cent, and this turn the data availability off for 50 and still less than 1 cent. So I think it's pretty good number. I mean, especially with data availability, that means the protocol is as secure as the Ethereum itself, right? There's no trade-off in security at all. And if we find a trustworthy big name to support the DEX by auditing the data availability off-chain, we can achieve even higher throughput. So we are pretty excited about this. Okay, so this is the design. So the idea is really simple, very similar to zk rollup. So basically, you move most of the data off-chain, most of the computations off-chain into a Merkle tree, a single Merkle tree. So the Merkle tree has 3 parts. The top part is the account. So you have multiple accounts as the leaf. Underneath each account, you have multiple tokens, and under each token, you have multiple orders, right? So this is a single sparse Merkle tree that you have to update off-chain, right? By updating off-chain, I mean you have to take care of those requests from either on-chain or off-chain. For each request, you do the calculation to make sure the root is eventually updated. So right now, the Loopring 3.0 supports the following 6 different types of requests. But actually, we simply need to support these 3 to make the DEX fully functional. So the off-chain withdrawal order cancellation and transfer are really optional. So the way we handle those requests is to batch those requests together into a block. So this is like virtual block. It's not the block of the Ethereum. So those virtual blocks got processed as a batch to update the Merkle tree. And after this block, we have a new Merkle root for the block. It's the post-processing Merkle tree root. We then submit this root, which is 32 bytes on-chain. So that's the only data, well, with some metadata. But this is the major part of the data that need to be submitted on-chain. So the computation is almost 0. And we just need to pay the gas for those 32 bytes, not bits, sorry, 32 bytes. And then off-chain, when we update, after we process the requests, update the Merkle tree, we get a better sense of how we updated those Merkle trees. So those data are going to be formatted into something we call receipts. And use those receipts, we run the prover to generate the final proof. Okay, and then we submit the proof. So I'm going to talk about the proof verification later. But when we batch those requests, there are really two ways to do that. And the first way is to group those different type of requests into blocks. So those are like virtual blocks, right? It's not the Ethereum block. It's our DEX block. So you batch those requests based on the time they come, and then you process them. But this turns out to be really bad because we learned the circuit, the zero knowledge proof related computation, is really not good at handling the dynamic numbers of requests. Sorry, it's not really good at handling like different types of requests, because that will make the circuit really big, and the proving time is like multiple times than it should be. So this is a terrible design we tried. Actually, this is what we did, right, as a final result. So we actually batch requests of the same time together, same type together, so that the circuit, to handle this type of request has nothing to do with the logics that handles the other type of request. So by doing this, the time to generate the proof is minimized. So we can effectively reduce the proving cost. So this is the way we chose. Okay. And the second point is that circuit is not really good at handling the dynamic arrays. So we have to only provide a fixed size of different blocks for, let's say, for this settlement, right? So we can put like 32 requests in one block or 62. You cannot put a random numbers of blocks here. So request in one block. If we don't have, let's say we have only 120 requests, then you have to zero pad like 8 default requests there to make 128. So the circuit will iterate 128 times. It cannot iterate a dynamic number of times, right? So this is some restriction of the circuit. I don't know whether this is going to be like a solution to fix this. If we have a solution, then we have one single type of block. Right now, for this type, we have different sizes, right? All right. So as I said, it turns out for ETHDEX, now we have a virtual blockchain on top of Ethereum mainnet. So as I said, we don't use like set change. So these are actually on Ethereum. The data for each block is 32 bytes with some metadata very small. So you don't know how many by looking at those numbers, you don't know how many requests are included into this block, because no matter the number, regardless of the number of requests, this size is fixed. It's very, very small, right? So in theory, we can even put like more requests in a block, but there are some restrictions in Ethereum that don't support that many very large batch of requests. So this is the only data, very, very small. So if we turn on the data availability for off-chain settlement, this green block, you have to provide extra data to make sure everyone can use this data to reconstruct the Merkle tree, right? For on-chain deposit withdrawal, you don't have to do that because it's on-chain already, so the data is available on-chain. So only off-chain requests needs to provide like extra data for data availability. And this is really has something to do with the number of requests. So the more you have, the more requests you have, the more data you need to put on chain. All right. So when the block has been submitted, after block submitted, you can run the prover. Once a proof is ready, you can submit the proof to a block, and the proof is going to be verified on-chain using the verification key. So once the proof is verified, this block is going to be, the status is changed from committed to verified, okay? And if a block is verified and all the previous block has been verified, then the block becomes finalized. So finalized means this block cannot be reverted at all. So it's final. It's truly final. This is like blockchain level final. So previously, I said that we want to achieve the settlement finality, right? Like instantaneously finality. But that finality is like, it still can be reverted, right? It's like a centralized exchange level finality. But here, if once we got a block finalized, it's finalized. So it also means if, let's say this is the withdrawal, right? If the withdrawal block is finalized, that means people can actually take money from the smart contract. All right, this is like finalized, okay? So what we can learn from this, so we can always commit blocks in sequence, right, one by one. But the proof itself can be submitted out of order. You can submit you can submit proof for him, and then for him, and then for him. So it's can be in different orders. That means, generating the proof can be paralleled, because it takes like hours sometimes, right, to generate a proof using a not that powerful PC. So if you can parallel the proof generation, you can use AWS to do a lot of work in the same time. So this is very, very important for us to really truly scale the DEX. Otherwise, the on-chain part is scaled. If the off-chain part is not scalable, then it's not truly scalable, right? So, so this is what we have done. And then we also applied some delay, the max delay between a proof submission and a proof verification. Sorry, the block submission and the proof verification. So there's like a maximum like 2 hours. I cannot remember the exact number, but it's during that time, if you, after like 2 hours, if you still don't have a valid proof submitted for a block, then you got penalized. The DEX operator got published, sorry. And their stake may be partially or even fully burned. We also want to enforce the DEX operator to handle the on-chain deposit and withdrawal requests, because that's really important for user to be able to deposit, and then their balance is got updated in a timely manner, right? And for withdrawal, if you submit a withdrawal request, you certainly want to get the money out of the DEX in a timely manner. So we end up having like two very small, like it's like on-chain deposit and withdrawal section. It's not really the section, but it's kind of like that. So they are hashed, so they linked together to make sure later when we process those events, it's the data modification is really minimal. So in general, we also applied a max request age. So if a request is submitted on-chain and the DEX operator don't really handle this request within this time, the DEX operator is going to be punished. So there's a time limit. To avoid a Sable attack, we also have applied another restriction for the number of pending on-chain requests. So you cannot, as a user, cannot submit on-chain requests if there are already too many requests. Otherwise, one bad thing may happen is that a lot of users submit a lot of very small, tiny on-chain requests, and the DEX operator don't have time to do the settlement. All they need to do is to handle on-chain requests, because there's a punishment if they don't do that, right? So this is to avoid that kind of attack. Okay, so if something bad happens, if the DEX operators don't really fulfill their duty by processing requests, or they submit some bad data on chain, which is not valid, verifiable, then the DEX will go to a withdrawal mode, which basically tells the DEX you are broke, you cease operation, you have to return all the money back to your users before you can get all the stake back, right? If the DEX operator don't really care about the stakes, they will do nothing, and after a certain amount of time, anyone can, because we have data availability on chain, anyone can reconstruct the Merkle tree, and then by providing the Merkle root, you can also get your money back, right? So in the future, we are going to sponsor someone to build a tool to reconstruct the Merkle tree based on the on-chain data availability to help users to get their money back if the DEX operator is not is doing something evil. Okay. We also introduced a maintenance mode. Because we have so many different type of restrictions to force the DEX operator to process user events in a timely manner, if the DEX operator wants to upgrade their backend, they will say, hey, I need to stop, right? So this mode is just for DEX operators to do something to maintain their backend, to stop operation for a certain amount of time. So the DEX operator can buy the maintenance time. So it's not free. So the longer your operation is stopped, the more you have to pay. So I think this is very necessary for DEX operators because they need time to upgrade their systems. So in general, Loopring 3.0 inherits a lot of cool features that I haven't even talked about from our previous versions, right? Like other aliasing, like anti-front running, partial order matching, etc. There are a lot of cool stuff. We also introduced a trading key. So that means your order don't really need to be signed with your private key, your Ethereum private key. So once you create a DEX account on some exchange, when you do trading, you can just give your trading key to your whoever is managing your account, right? You don't have to give them the private key of the Ethereum account. Right now, I would say this is still not production ready. A lot of things can change, can be optimized. So with zero knowledge proof, especially zkSNARKs, we need a trusted setup, right? This is not good, right? So hopefully we don't need to do the trusted setup. So thanks to Sonic, so in the future maybe we can just share a trusted setup among all the DEXs on Ethereum. Right now, we have to verify every single proof for each block, which costs $500,000 gas, right? It's pretty expensive. So maybe we can, generate STARKs, 4 STARKs to make it recursive. So we can probably only run the verifier on chain for maybe every 1,000 blocks to reduce the gas. The other one with also what we're looking forward is the cheaper storage on blockchain. As Vitalik has acknowledged, that right now the storage price is too high, right? We can, hopefully the Ethereum will reduce the cost, so we can put even more settlements in one block. I think the most possible optimization is GPU-enabled proof algo, right? So if we make it run on GPU, then it's going to be a lot more cost-effective. So a lot of things that can be done on top of 3.0. So right now we are making the 3.0 code really production ready. I think we are still not ready to compete with Binance, the top tier sexes, right? But to compete with small ones or even the mid-sized ones, I think I'm pretty confident because this is really secure. You as a DEX operator, you don't have to invest a lot of money in internal security measures, right? So it's a big win. And for normal users, this 3.0 its user experience is really similar to the centralized exchanges. You have deposit withdrawal, you have your trading keys, trading is like the trading password on Binance, right? So the user experience is much similar to Binance. So this is Loopring 3.0. We have open sourced our code like 2 or 3 weeks ago. The code, the smart contract has not been securely, has not been audited yet, but we are working on that. So our plan is to launch a beta version maybe later this quarter or next quarter. So we really look forward to that. So this is 3.0. You guys have questions? Well, you can go ahead.
This is a very high-level question, but it looks like they're not like side chains, but your Merkle tree, all that data you're storing off-chain, and then when you commit, you just commit the root hash. Is that right?
Yes.
And then these are very basic questions, but so you're a protocol to enable other people to operate DEXs, but you yourself are not a DEX.
That's true. So we have a parent protocol contract. So use that one. You can call a function called create DEX. Then boom, you have a new DEX. So everything is yours, and you are responsible to. You can choose to stake some tokens there. Say, hey, I have something to lose. Trust me, because if I'm not, if I do something evil, then I lost all my stake, right? Yeah. So basically, we don't want to run the single best DEX. We want to open source this. We want to help you guys to run DEX. Yeah, but we will probably also run the DEX, but it's not exclusive. So the business model is probably different from stock DEX or something, right? Yeah. Mm-hmm.
The zkSNARKs they provide some privacy. How much privacy do they provide? Because I know you're committing approved on-chain settlement at the end, so maybe you can seal individual trades within a block.
Well, we use SNARKs for scalability, not privacy. So with data availability, everything is available on chain. All the transactions, all the settlements, you see the data on chain. So it's as secure, as transparent as the previous versions. Without data availability means you can always request the data off chain, but you should have access to all the trading data. So there's no privacy here.
You guys have 1 more minute.
Sure, thank you.
Well, we can talk after.
Yeah. So no privacy. Privacy is not our focus, and we even think privacy may introduce some regulatory issues here if we want to trade security tokens in the future. So this is not related to privacy at all. Yeah.
So we need to ask.
Yeah. All right. So that's it. So thank you. Thank you.